All right, well, thank you everybody for coming today. My name is Scott Stender, and we're going to speak about blind security testing and an evolutionary approach to that was a piece of speaking about. Start off with who am I? I'm a co-founder and vice president of Bicep Partners. We are a consulting company primarily, but also a product. And in my personal role, I am primarily a security consultant and researcher. I work primarily on application security. So in my day-to-day job, I'm doing design reviews, helping people figure out how to create their products securely, and doing a lot of testing, and putting in creation of a lot of test tools. And some of the experience I've had on that is what I want to share today. And I'm based out of Seattle, Washington. So why listen to this talk, and who should listen to this talk? I think you guys can feel free to head out right after I get done with that. But the purpose of this talk is because a lot of what we do as security practitioners is creating test tools. And I will say that security, especially software security, is very difficult to test. And the people who are going to get the most out of this talk are people that are writing test tools, running test tools, in charge of creating test tools. Basically, anybody who has part of testing software as their goal. And I'm terribly sorry we'll not have any high-profile bugs today. This will be all about theory and construction of security test tools. So the title of the talk, Blind Security Testing, an Evolutionary Approach. So blind security testing, why is it useful? Why am I talking about it? Well, it's useful because in my day-to-day job, I find it is something that we need to pull out from time to time. I think anybody will agree that the more information you have about the system, the better your security analysis of it will be. And that's the case in terms of being able to get white box analysis of, getting source code, symbols, being able to do debugging and code coverage, and all those things are very helpful for a comprehensive security assessment. But even so, blind security testing happens when you have distinctions between the engineering and the audit side of things. So in one of my recent projects as a consultant, we were hired by a large e-commerce company. And this company wanted us, and we were hired by the audit team, not the engineering side. And this company wanted us to do broad testing for audit compliance purposes across a number of their worldwide sites. So they had a USA site developed by one team, a Japanese site developed by another team, same with Europe, Asia, Africa, all over the place. There are probably about 10 different sites, all of which were developed differently. And testing for all these different sites in a blind security testing framework was rather difficult. There was, different coding styles, different problems that we were finding. We found the USA site was mostly susceptible to cross-site scripting. The Japanese site had SQL injection all over the place. This was all stuff that we had to determine using only blind testing techniques. So the ability to have smart fuzzers, smart testing frameworks that are able to act based on only what the system is responding with is something that's still useful today. But the big problem with that, and one that came out of my last year's Black Hat talk, where I spoke about internationalization, is that there are a number of test cases out there that we can find, and actually a near infinite amount, and optimizing those to be the ones that are most likely to cause security flaws is something that's very difficult, and the real crux of this talk today. The talk proposes a method of competition between test classes and test cases within those classes to optimize those test suites, and that's where the evolutionary part comes in. So this talk will be in 3 parts. The first is background, where I hope to prove to all of you that optimization is necessary, it's important, and it's something that we're going to have to do if we're going to move forward as a security industry. The next part will be current approaches, things that I've seen people employ to optimize what they have today and be able to, without anything that I'm proposing today, actually make more optimal test suites. And then the last part is what I'll propose as a framework for, making smarter testing suites. There's an implementation of this that I'm working on, but it's not ready for public release. But when that is the case, I will release it. So I'll head into background. So problems testing software. The big problem is that even trivial applications can generate near infinite test cases. And even forgetting about security for a moment, just doing basic functional testing, one classic example of that sort of trivial application with a lot of tests was proposed in a book called The Art of Software Testing, which is a rather classic book in software testing, where the author, Glenford Myers, put forth a program with 5 logic paths wrapped in a do-while loop. And that loop would execute from between 1 and 20 times. So we have a little control graph that illustrates this. On the top, we have the begin state. We go through a number of conditional choices that could be driven by user input, system state, anything you want. The big thing that we're worried about is that at the bottom, we get into 5 states, A, B, C, D, and E. You could call those the output states. So when the program hits there, it says, hello, my iteration, printed out A. And then we go into the end loop. And then we terminate after between 1 and 20 executions of that logic flow. So this simple example can be represented in 10 or 20 lines of C code, or one really nasty line of Perl. And on each loop iteration, output will depend on those 5 input states. So we could say that one output of this program would be the letter B, if the loop only iterated once. If it iterated 5 times, it would be B, C, A, D, E, or something along those lines, and on up to a string of 20 characters. So if we were to have our test suite optimized around, we want to test every potential output of this application. If we were to test for 1 iteration, it would be 5 outputs that we'd have to test. 2 iterations, we'd have 30 potential outputs, 5 to the first plus 5 to the second. And if we were to go to up to 20 iterations, what Mr. Myers put forth, we'd have 100 trillion test cases. Which if we were to execute one of those per second, starting now, it would take 3.2 million years for that test suite to run. And our evil robot insect masters at that time would be very happy with our output coverage, but they'd be unhappy because they could not say that the program was correct. Because even if we've covered all the output, that is not necessarily something that assures that we've covered all the input or all the internal state. What happens if we run that again on a hot day or a hot 3.2 million years? The CPU might act differently. We might fail in another way. And if we were to think back at this same flow, this might be something that builds a number of different database executions. So, we would output, hello, this table should now have a new row that says A. This table should have a new row that says B. We could cover all this comprehensively, have 100% output coverage, 100% code coverage, and still never find the SQL injection in that. So there is a lot that we are not taking into account in terms of system dependencies and all those other crazy things. How hot it is today. If 10 inputs map to 1 output, the big takeaway is that we have a lot of functional tests to execute. Now, security testing is even harder, because what we looked at just there was an exercise in functionality alone. And security testing has 2 aspects, both functional testing and I would say non-functional or negative testing. So a functional security test case would be something like logging in to a web application. So we're presented with a form, username and password. There are 4 states we need to check for. There is, if I put in a valid username and password, I should get access granted. If I put in an invalid username and a valid password, I should get access denied. Same vice versa. And if I put in a valid or invalid both password and username, I should get access denied. So there's my functional test case for making sure that my authorization or authentication mechanism works properly. So all right, 4 cases, I'm done, I can go home. But then there's the non-functional aspect of it, where the assertion we need to do is that there is nothing under the sun that can possibly make one get past that login page and access the website without typing in a username and password. And so that involves not only trying those 4 cases, but also every piece of input, every system state, every environmental condition, anything that could possibly result in that not working. So we have, in addition to the 100 trillion test cases we spoke about a moment ago, we have a potentially even more infinite, if there is such a thing, but a near infinite set of test cases of everything that could possibly happen to that site. So we say, we have patterns. We know that if we want to get past that front page, there are things we can do like SQL injection, buffer overflows, session hijacking, a number of attacks that as security practitioners we test for. So let's go and drill down into one of those things that we need to test for if we want to have a comprehensive test. So buffer overflows are great goat because they have been known for 30 years. They've been taking down the internet for almost 20 now. And it's something that we all test for and we all see on the news headlines every day. So what do we do when we want to test for buffer overflow? Well, the first thing is we show up and we ham-fist the keyboard for a while and make a string, hit enter, and see if it blows up. And it's unfortunate that a lot of times that is the case. But if we want to be a little bit more comprehensive, what we do is we supply a number of long strings, 128 bytes, 256 bytes, 65,536 bytes. The big thing is that there's a bunch of magic links around powers of 2. So if we say, we're going to try, powers of 2, 2 to the first through 2 to the 32nd, and a few magic numbers around that, hey, that's a pretty good test suite. We send a bunch of A's into it. Well, I've actually heard of application developers who have a consultant or an external researcher find a flaw where they put a bunch of A's into a buffer and they show that EIP equals 41414141. So to fix that, what they do is they check for AAAAA and then kick it out. So if you want to test for that as well, and that's a real story, but if you want to test for that as well, you have to test for BBBBB for those same things, right? And then what happens with all those other off-the-wall things? Those of us who've been in code review for a long time have seen those crazy structs where there's 436 bytes to a struct, but if but there's a validation routine that says, hey, if this thing is greater than 430 or 440 bytes, then we'll kick it out. And so there's this magic number of 437 to 439 byte strings that will cause an overflow and cause bad things to happen. So we have to test for all of those too, right? And then there's pattern-centric stuff. So if the first byte must be, in order to get that buffer overflow, the first byte of the string must be hex 1E. And then we must have a file path after that. And then the subfolder specified in that file path must be over 64 bytes in order to overflow that. So you have all these crazy things. If we really wanted to come up with a comprehensive buffer overflow test, clearly this exercise could go on and on and on until we have, yet again, another near infinite test set. And then that's just for buffer overflows. Next up is SQL injection, XML injection, cross-site scripting, attacks against custom serialization, all the other things that we find on a day-to-day basis. And then when we're done with those, don't forget random fuzzing because we find bugs with that too. And so you have a energy in the universe amount of testing you can do with random data. So what I'm trying to get across here is the need for optimized test suites. We cannot test everything. Anybody who says that we can do a comprehensive security test is lying and selling you something. So let's get away from that. What we need to do is be smart about the tests that we perform because in every instance there is a logical limit of the amount of effort we can perform, whether it's money, time, anything. We have to find the most bugs that we can in the time that we have. So if we were to think about optimized test suites, we know that today experienced security testers do this. So go back to the web application test, which I will go back to that a lot because it's a great familiar framework to discuss these flaws in. But the first thing that any security tester does when they show up at a web application is they type in an apostrophe into that login form. And if it blows up, you see a SQL exception, then hey, great, I found a bug. And the second thing people might do is type in ZZZZZ or some other recognizable pattern into the username and then see if it gets reflected back to them. And if it gets reflected, then hey, I'll go start testing for cross-site scripting attacks. Today, as security testers, we do a natural optimization. We know that a web application is going to be probably more susceptible to things like SQL injection, cross-site scripting, cross-site request forgery than it would be to buffer overflows because most web applications are written in managed languages. So this optimization happens today, but what we want to do is be able to see if we can automate it, make security test frameworks smarter. So I hope everybody's convinced that security testing is hard, that there's a lot of work to be done, and that we need to optimize things. Now, I'm not the first person to realize this, so we're going to go into current approaches. A lot of other smart people have been working on this for a lot longer than I have, and so we'll see how other people have approached this. So if the goal is optimized test cases, then we can look at most security testing tools and realize they pull from two rather large pools of test cases. First would be flaw-specific testing. The second would be random-based testing. I'll go into that a little bit. So with flaw-specific testing, the goal is to identify specific known classes of flaws. So for example, SQL injection, if I were to do a flaw-specific test for that, I would say, my test case is find a parameter in some web request or arbitrary request that might have a database behind it, put an apostrophe in it, and if I see an exception come back or some other undefined system behavior, then I think that, maybe that's a bug. Maybe I'll go file it as a bug with the developer and have them investigate it. Something like that. But there's a very clear case and result, and we're looking for a very specific flaw. And so we can look at flaws for a number of classes of test cases for a number of classes of flaws, and here's an incomplete list. But if we were to put them on a pretty graph, they'd look like this, with test suites along the left, and then test cases, again, incomplete, just for example's sake, on the right. But for buffer overflows, we'd test a lot of A's. For format strings, we'd test a few well-known format string parameters. For integer overflows, we test, numbers that are, again, at the magic numbers or magic parameters of 2 to the power of something and around that. Cross-site scripting, SQL injection, and so on. So what we do is put all those in the parameters, and the benefit of such tests is that they are surprisingly effective. As a security researcher or tester, you can look back on your experience and see that you know what, I've done stupid A test into various inputs, and I've noticed that there are a number of times when I've had EIP equal 41414141 after that. I've put a number of apostrophes into login fields, and I've seen a number of SQL exceptions, perfectly crafted to let me know how I can exploit it better. So they are surprisingly effective still, and they are easily prioritized over random input. Consider what you'd have to do if you wanted to find cross-site scripting based off of pure fuzzing. And by fuzzing, I mean sending random data or random mutations of data, and having all those monkeys typing out the works of Shakespeare and my test data come up with script alert hello script. That would take a very long time. So they are very easily prioritized, very optimized, and it's something that, again, security researchers take that knack of what might be behind the scenes and test upon that. The drawbacks of flaw-specific tests is that, for the most part, they will not find any flaw other than what we expected. If we were trying to find SQL injection flaws, it shouldn't be a surprise if we don't find anything else but SQL injection flaws. Obviously, there's some overlap in the test data, so we might find a couple of things, but for the most part, we're not going to find some goofy back-end serialization that delimits its data based off of commas as opposed to databases or web services. So we're pretty much stuck in what I would call a local optima. So we're getting into the evolutionary stuff later on. And I'm sorry, I actually should have done a little graph on this, but if you think of, a lot of algorithms try to find optimums of a value or minimums. If any of us are computer science backgrounds, are no stranger to that. But you could think of finding just a specific SQL injection flaw as finding a local optimum on a big graph that goes up and down. It's one kind of flaw. There are other kind of flaws to find out there, and if we focused all of our time on finding that one, we'd be in trouble. So the alternative, which is a bit orthogonal, has great attributes that are not in common with flaw-specific testing, is random testing. The goal of random testing is to see how the system acts when subjected to random input. The difficulty of making tests on random input that we did not create is we also don't necessarily have ways of identifying when it goes wrong. The canonical thing to do is to attach a debugger, start your random fuzzer, and wait for a crash, which is great for finding one type of flaw, buffer overflows or other type of memory corruption errors. But it's not going to help you find that SQL injection in there or that random cross-site scripting or anything else. So the goal is to just find out what is necessarily bad behavior, and we hope we can figure that out in advance. So if we were to do random testing, the major goal of that, or the three types of test cases that I've seen a lot of people pull from are pure random data. So if we go back to our basic web application example again, if I just open up port 80 and start catting dev random to it, then that would be pure random data. And then there's parameter-specific random data, where I know that a web request actually has a number of inherent parameters in it, values on the URL, values inside of post strings, cookies, refers, any kinds of other things. I understand that those are parameters, and I test random data for those specifically. And then the third high-level area is random mutations of legitimate data, where I have my request. What I do is I go through the entire thing, and I flip random bits and throw it up there. I know that it's a legitimate request to begin with, and I'll probably get somewhat deep into the control flow of the parser for that request. Might even get back to the back-end business logic. But I have, because it started off as original or as legitimate, then I can probably get deeper, and maybe I'll uncover a flaw that way. So you can either do bit flipping or bitstream sliding to do that, where you'll hit the entire request. So back to the pretty pictures of three random-based test classes: purely random, parameter-specific, and mutation, and specific test cases that I would execute within that: random content, random length of content, same with parameter-specific, and then mutation, the two types of bit flip and bit slide. So the benefits of random testing is that they are surprisingly effective. Whether in 1990, when the original paper on fuzzing came out, or 2007, most of the bugs that we see that hit the front pages, including two of my fellow ISECers who presented at this conference, found these things by simple random test cases. It's actually a rather sad state of software engineering that coming up with something completely random and having that be sufficient to knock over $1 million projects or $1 billion projects. Pretty sad thing, but it still is effective today, even if we're getting better. But the big benefit of random testing over flaw-specific testing is that we avoid the problem of local optima. We're not going to spend all of our time looking at a specific thing like SQL injection or cross-site scripting. We actually have the possibility of getting outside of what we're looking for and finding that random comma-based serialization bug that's way down deep inside of a mainframe somewhere. The drawbacks of random testing is that purely random attacks are horribly inefficient. Instead of local optima, we choose for no optima. Starting off, there is no value that is going to be more or less likely to cause flaws. There's no smart heuristics we can necessarily apply. In the general case, we'll actually get into that in a moment. But you really get into some, if we were to, again, try to find that cross-site scripting with pure random data, we'd be in trouble. But again, we luck out because test cases are cheap and apps are bad for the most part. The test results are hard to define, as I hit on earlier. If we can't define what the behavior of the system under test is when a flaw occurs, and how can we be expected to identify that when we're running billions of test cases? Actually, we see that a lot with test systems where the main problem isn't finding flaws, it's actually sorting through the results of those flaws and trying to find out what is actually real and what is actually bad. So what do people do to improve security testing of these two types? Well, there's just using simple heuristics, you can improve things. You can do stuff like if it's a SQL injection type of attack, and we want to test for that, we can do things like remove equivalence classes. There's no need to test for every possibility of apostrophe with surrounding letters, when apostrophe is really the key thing that usually shows us that SQL exception that indicates the presence of a flaw. So we can do a lot of minimization of test cases. We can do some basic feedback on, hey, if we found a flaw, then move on, no worries. But with random testing improvements, actually the talk that was right before me, which I'm afraid I was not able to attend, but they actually spoke about using evolutionary algorithms to improve what I understand to be random testing. And actually there was a similar talk last year with Sidewinder, as I understand it, having not seen this year's talk. But I've seen a couple of security practitioners and academics use evolutionary algorithms to improve the quality of random test data. And I think that's very cool, and I think that's something that should be continued. The one thing that's obvious to say about that is that if both of these approaches were relied, as I understand them, primarily on debugging and code coverage, which requires interactive access. You need to be able to actually hook into that process and get information back to your fuzzing or your test tool. So the one benefit of a blind approach is that you don't require that. Okay, so any questions so far? We've gone through the background, the need for testing, and current approaches. We can go into the blind evolutionary approach unless anybody has questions. All right. Very understanding crowd. Okay, an evolutionary approach. So we've talked about the problems of local optimization. We've talked about how it's we have a intractable set of cases to choose from, and actually those two descriptions actually point pretty well to an evolutionary approach. Because what evolutionary approaches offer over other heuristics is the ability to jump out of local optima, again if we're going back to pure algorithm design, and be able to find things that we might not otherwise search for if we were doing a native or a naive type of search. They also can make sense of purely random data, as the other researchers have shown. And they also are good at dealing with large sets of test cases. People apply to things like the traveling salesman problem, which are very difficult to solve. And so this is the natural selection for this, no pun intended. First, a quick primer. Evolutionary algorithms use a biological selection as a model for computer systems. So we're all pretty familiar with the theory of evolution. Sorry to Kansas people. But the goal is that we take biological selection as a model for making things more efficient. So what happens is we start off with a population of things to try. This is the case whether it's a traveling salesman problem or a security test framework. We start off with our populations, and we try them against something as a solution to a problem, and we establish what is called a fitness criteria. How well does it solve the problem? That feeds back into selection of the next generation, which then gives rise to the evolutionary aspect of it. So you have starting populations, you try them out, you mix them, you keep on going, and if you are a good solution to the problem, you live on to see another day. But the difference here is my goal is to not optimize a single solution or find the maximum of a function. It's to actually create an optimal test suite. So whereas something's looking for an optimal thing like code coverage, I'm looking for an optimal chunk of things to run. So evolution and blind security testing. So instead of maximizing one thing, we're optimizing test sets. And then we use test case results as fitness criteria instead of code coverage or debugging. The reason why that this is beneficial is going back to the original slides in my talk. I spoke about how a lot of times as a researcher, as a consultant, I need to interact with systems where I don't have a lot of information about them. I can't assume interactive access. And so having generally available criteria as fitness criteria that I can compute on is very helpful. So the goal is to evolve an optimized test suite for a given request or a series of requests based purely on test feedback. So we'll start off with test case organization and competition. Going back to my quick primer, there are three things we need to do. We need to define populations, we need to define fitness algorithms and criteria, we need to define next generation selection. So for population design, an optimized test set is made up of several test cases, not just one case. So again, what we want to avoid is spending so much time on SQL injection because we found a couple that's the only test we run. We actually want to keep things such that there is a variety of test cases being executed, but the ones that are most likely to cause flaws are going to be executed more often than ones that are less likely to cause flaws. And as I mentioned before, this is good because one of the things that we assume is that a lot of applications that we write bunch together flaws. If I'm looking at a web application and it's written primarily in managed code, I really don't look for buffer overflows very much. I might try it a couple times, realize it's mostly a waste of time, and spend my limited amount of time trying to look for SQL injections and cross-site scriptings. So what I do is I optimize those and neglect the others to some degree, but it's always good to include them. So the population design of these different test classes and test sets or test cases within those classes is actually how that is addressed. Problem breaks down according to two questions. What class of test case do we want to test? And within those classes, which tests are most effective? So populations as test sets. So we went over during the intro of this talk the various test sets that we often execute as security researchers and practitioners. We have the flaw-based and random test sets. So each one of those test sets or suites could be thought of as a population. Basically, if we want to optimize a test set, then we want to tend towards SQL injection, away from cross-site scripting, something like that. This is where the selection comes in. These populations will be created using traditional heuristics, gut hunches, anything like that. I mean, as a practitioner, I know that there are a certain number of characters and patterns that I test for when doing SQL injection testing, so I'd create a test class of that and then several cases within that. And then the selection mechanism will look for the test class and then also the case within that to execute. And then you have evolutionary competition between the sets and classes. If SQL injection versus cross-site scripting tends to favor SQL injection, then I test for that more often. Against buffer overflows, I test for buffer overflows more often, and so on. The adjustment of that selection gets modified based off of prior results. So let's begin with the population selection. So those same pretty graphs we saw earlier are now in a horizontal fashion. You see buffer overflows on the left going over to random mutation on the right. And within there, random test cases, or not random, but specific test cases sometimes and random test cases sometimes, which trail off of those classes. So those are our populations that have to compete against one another. Fitness algorithm design. The goal of the fitness algorithm is to make fitness criteria accurate and determined by generally available criteria. This is where some of the blind security testing comes in, and why I focus on that as this talk. But other approaches, I mentioned before, profiling via debugging or coverage, also things that you might want to look at are log entries, system logs, stuff like that. Even in the one difficulty of going straight for the debugging and code coverage, we hit on earlier on, is that though code coverage is a great metric for how many tests you're running and how much code you hit, as we showed earlier with the logic flow, it's not a 100% accurate way of determining test coverage. You might be following every logic flow, but you might still have a SQL injection in there that isn't part of what you're measuring. It might be in a system dependency. And then also, it's again, if we require interactive access, it's not broadly available, and that's a question back there.
Yeah, I would say, I would think that probably code coverage would help define how much tuning you can do, because if you don't test a particular branch, you'll never see the security flaw there.
Absolutely. And I'm actually not arguing for this as being a approach that is going to be necessarily better, just more generally usable. And where it's applicable, I would say definitely the more information you can get into a fitness algorithm, the better of a selection you're going to make. Any more questions? Okay. But yeah, so that's the downside. The major downside is that if we were to optimize purely for that point, we would not necessarily have an optimum test set. And that's where a diversity of criteria come in, and then also that it's not generally available. So another design, or you could say an additional criteria, would be to use system feedback and the natural properties of test cases. So system feedback, what we can do is as we are generating our test parameters, the requests that we're going to test, we can keep control information about each request or parameter that we're going to test. When there is nothing evil happening and I make this request, I know what the response is going to be. So when we start doing evil things, when we start putting nasty data in there, when we start making random mutations, we can identify a difference from control, and I would call that the magnitude. And also if you have flaw-based testing, like the set of specific characters we use to test SQL injection, then we can also use more sophisticated methods of error detection. I'll go into that in a moment here. Oh, forgot the picture here. The big thing here, though, is as we're building our evolutionary system, we still have those same cases. They go into a test engine, along with the request to be tested, and then the results of those tests go out of the test engine, and then feedback from the results comes back into the test engine. That's where the selection comes in. We'll talk about the selection criteria in a moment. But if we want to see how this works in the real world, consider a web application. And you capture that legitimate request. We know the control. We make a security test case. We put that apostrophe into a parameter. There's two things we're going to measure: the magnitude of change. Now, the magnitude of change would be the size of the data that is added. If we do a diff between new and old, the size of what was added plus the size of what was removed. Now, I will argue that this is a good thing to verify or to look at as a fitness criteria. Because it's effective, broadly applicable, and even fuzzing, we will recognize that if the system stops responding, that this is something that is going to generate a magnitude of change, whereas once it responded, it does not anymore, and that is going to say, hey, this is something bad happening, we'll check it out. And then also just think back to experience, where if any time I put in a apostrophe into that login field and I get a cross-site or a SQL exception back, what do I see? I see what was the original page that maybe would redirect me to my logged in console, or maybe the access denied. I'll see that page go away, and I'll see a big exception trace come up. Or I'll see that page go away, and I'll see a error, non-determined application thing comes up. And in all cases, not in all, but in most cases, we will see a significant magnitude of change. And this is a pretty good, broadly applicable way of determining if something requires more search. Again, this is not trying to identify the exact flaw or line of code. This is fitness criteria. It's saying what this causes more change to the system than legitimate data does. That's actually the second thing I was going to go into here. There are two broadly available fitness criteria I would say should be addressed in a blind security scenario, and we can go into others in a moment, but good question. The second one would be error detection. Now, if we're doing flaw-specific testing as some of our criteria, or our test classes, then we also understand the specific, a lot of what we should expect when it comes back. So like you mentioned, cross-site scripting. If we go and put some determined pattern into a request, ZZZZZ, and we see it reflect, then we can say, this is reflected data. Let's see what we can get through. Apostrophe, quotation mark, brackets, semicolons, things that you would use to mess up the HTML document or JavaScript code that you're seeing this data reflected in. It's going to be dependent on where you see the context of where it's reflected. And you can test for that. You can see that, I'm seeing some things that I don't necessarily want to see reflected. And then you can also have that be fitness criteria. So for each of the flaw-specific tests that you put into this system, you would have a pluggable framework of this is the way you look for flaws. And so you can get very sophisticated with that as well. So SQL, for example, SQL injection, what I could do would be not only just wait for the SQL exception or the non-specific error returned, what we often see. I could start moving into blind SQL injection techniques. I could try the 10, 15, 20 different ways in which you can often complete out a SQL statement and see if you can make it return not the error, but something different. And often when I'm doing blind security testing, that's exactly what I do if I want to verify. I'll start off by putting an apostrophe, and then I'll do apostrophe and then comment characters, hyphen, hyphens, or the like. And if I see that happen, I say, you know what? I was able to get an exception by just an apostrophe. I messed up the SQL statement. I was able to do hyphen, hyphen, and get it back, and nothing, I didn't see the error anymore. So you can put a lot of intelligence into that. And the same can be said for just about everything. So then choosing the next test. So fitness criteria adjusts the natural priority of test cases. So I've hinted at this about 1,000 times already, but what happens is each suite of test cases, or for flaw-specific testing, random testing, whatever, is assigned a default probability. And when we start seeing these test cases come back successful in finding what is likely to be a fault, or we could be more general and say a major change in system behavior, then we emphasize both that test class and then make that specific test case more likely to be executed. So what we'll have is, over time, that probability shift towards classes of flaws that are more likely to be present in the application as we go on. And again, this has a major assumption that flaws tend to be shared across a large component or application. And this is a viable assumption because a lot of times these are created by the same developer or same development team with similar coding guidelines, similar technologies. So it seems like a good assumption to take, and one that helps us create broadly defined evolutionary fuzzing systems or security testing systems. So note that one thing we never do, one thing I would rather avoid doing, is to remove a test case or class of test cases. Because one of the original goals is to not simply have a SQL injection test framework. We can write one of those rather easily and not have to say anything about evolutionary algorithms inside of it. What we want to do is make it so that we optimize test sets so things that are more likely to cause flaws will find flaws, but that on occasion we still have the chance to find that random flaw based off of some random character. The end result is that cases compete for execution time, and better cases move to the top, both within classes and the classes themselves. So we go back to that again. What we see here is the same graph that we looked at a moment ago, except for we now have probabilities on there. And on this particular run of test cases, we'll see that hey, buffer overflows and format strings have been de-emphasized. SQL injection is way up there, and so is cross-site scripting and random testing. And that's just a lot of what I've seen when I'm doing general web application pen tests. Now, one thing to call out as a potential issue is test set stability. So if we were to leave this by itself, then one type of application that might cause some problems are, let's say we have two friends creating a web application. And the one really likes .NET, and the next one really likes C++. And so they create the worst architected web application ever. And half of it is susceptible to cross-site scripting and SQL injection. The other half is subject to buffer overflows and format strings. So what you would have is, as you're testing request number one that emphasizes our friend that wrote it all in .NET or Java, and we start really skewing towards SQL injections, cross-site scriptings, and other things like that. And then as we moved over to the friend that wrote all in native code, we'd start seeing all these buffer overflows, and we keep on going back and forth. And actually, it wouldn't be terribly efficient because we'd have to do the build time on each request to actually recognize that things are more likely to be buffer overflows and move it over there and go back and forth. So one option is to reduce the temperature. So temperature is a reference to another concept in algorithms, especially in simulated annealing, where you have a general parameter that defines how likely test cases, or not test cases in this case, but how likely you are to change the probabilities or the search criteria or things like that. So over time, what you'd have is when you start the test run, all the percentages are equal and very likely to change, and then after 10,000 test cases or so, they're much less likely to change. So what will happen is over time, because things are less likely to change, you'll settle out to a 50-50 between our Java friends and C++ friends. So that would be something that if you see that thrashing, that you can put in there. It's not been something that I've necessarily had to do because I haven't run into one of those applications. So the conclusion is with an evolutionary approach, We can use traditional test populations, things that we use we know are effective today, to find flaws, but also benefit from from random testing and from a number of other advances in optimum security testing. Put it into a single framework where it will self-organize around being able to use the most optimal tests that we do today in order to test systems. The benefit to this approach, especially if we keep it blind, is that it's broadly applicable to a number of systems and test criteria, though of course we can always make it smarter, and you always should, depending on what you have at your disposal. But if we keep it blind, we do not require interactive control in the process being tested. The drawbacks is if we keep it blind, again, we will not have the smartest fitness criteria, and so we'll have to run it for a very long time, or longer than if we had all the information in the world, to actually have it come across an optimal test set. But again, if we don't have the ability and we have a lot of time, then that's not a necessarily bad thing. And then one thing that rubs a lot of people the wrong way is that in the end we have test cases that are not optimal or comprehensive, just optimized. What happens after you run this? And this actually happens with a lot of new testing techniques that don't rely on static test sets that a tester spends several months writing. Is that, okay, I ran this. I ran it for a week. I ran it for a month. What did it find? What coverage do I have? People will say, did you test for cross-site scripting? Well, yes, the thing did test for cross-site scripting. Up to 17% of the tests were based off of that. Did you test for this specific thing? Well, you can never answer that. And that rubs the people a lot of times the wrong way. The big thing I would say in response is that there is no such thing as comprehensive testing, that we really need to do the best we can with the time we have to test, and that though it's a bit of a shift to think about being optimal in this way as what we should be doing, it's something that if you think about it for a moment makes sense, even if we don't have a set of static test cases. And we can also put very high probabilities on those things that we always want to run, like apostrophe for SQL injection, to make sure that for the most part they get in. So what I presented here is what I have implemented and will release at some point in the near future. But there are certainly many things that I have not yet implemented that would make it much smarter and much more applicable. And I think there's a lot more than what I have even on this slide to make it better. But the best thing you can do is improve your fitness criteria, both in terms of integrating things like code coverage and log analysis. Of course, would help make things smarter. But also, I mentioned advanced flaw-specific testing to make sure that to improve the degree of confidence we have that when a flaw-specific fitness criteria fires back and says, you know what, I found a SQL injection, I'm pretty sure. The better we can make that, the better the evolution will be. We can also do improved breeding. What this approach that I presented here looks at is primarily parameter and request based. I did not mention much about taking into account state as an input to your test systems. But of course, the more that you do, the more that we take that as an input, we can do things like have going through 3 different requests and having state be propagated across them, and having that be something else that we take as a fitness criteria would make it much smarter and better. And then also stateful tests. Just mentioned that. I should look at my thing more. So special thanks for offering their time and feedback from Brad Hill of HiSec Partners, Andreas the same, and Tim Newsham the same. They have helped me with a lot of bouncing ideas and helped the tool very much. And then also, if you look at the white paper that accompanies this talk, I did mention a large number of cited academic and security practitioners that have been working in this area, whether it's pure evolutionary algorithms or people like my previous presenter who spoke on gray box fuzzing, or last year's Sidewinder people. There's a lot of great ideas out there, and it helps to be building on that. So questions and answers. I've gone a little bit short. I anticipated more of the questions, but we have a good half hour if anybody would like to talk further. Thank you. Oh, yes.
I do have a question. Isn't the main criteria of the quality of the tests the question what kind of feedback you actually get back?
Mm-hmm.
Because I think, just to follow up on your example with the SQL injection, if you actually have a SQL injection but the exception that's being thrown is being caught, and you're just being redirected to the login page, for example, this is something that you're not going to notice as feedback on the application. So you might as well schedule that type of test back, when in fact the code flaw is still there.
So the question was if somebody, to paraphrase, if somebody, this approach could be fooled if one were to have smarter exception handling to make it so that one would not necessarily see the exception trace or the dirty words that one often sees with that. Is that fair? The one thing I would say there is that that's actually why I would propose both the magnitude of change as well as the flaw-specific change, because even if you did not see the specific ODBC word or anything, or JDBC or error, you would see that behavior was significantly different when you put an apostrophe in or another SQL injection dirty character versus when you put in the letter Q. You would notice that, probably another question. So that would be something that would still benefit that, but of course it would be less efficient than if you absolutely knew that there was a SQL injection there.
Yep.
Any more questions?
Cool, thanks, man.
Oh, right in front. Mm-hmm.
I'm not wondering, are you testing mainly testing towards website? How about other applications, which it's hard to validate the end result?
The question was that many of the examples I cited today were based off of web applications and flaws that tend to affect web applications, and what would happen if we were testing an application other than a web application. Is that fair? Paraphrase? Okay. I would say that many of the flaws that we're looking at here, or the general approach would still apply. If the endpoint was an RPC server as opposed to a HTTP web server, then I would still be able to see magnitude of change. It might occur that the server simply stops responding, or it responds with different data, but I would still see some big change. And of course, if I were creating the error-specific flaws and things I normally look for in RPC interfaces, then I might architect those so that they would look for specific RPC error codes or things like that. The key thing is that from an architectural perspective, you can usually come up with things that are broadly applicable on both of those. And of course, if you do have interactive access to the system, then code coverage, debugging, log analysis, all these are the things you could feed in, which would still be applicable. But the general framework of understanding your classes of tests and choosing from them would still apply. Mm-hmm.
Just put all the test case in a big XML file.
Mm-hmm.
That's normally what we do. And how could you help us to, for example, we can redo our test cases. So how do you interact with what we have right now?
Mm-hmm. The question was that right now the team that she works for has a large set of test cases in an XML file that they execute on. Is it just a static test suite that you run every one of them in there and then? Okay. Well, I would say that there's no harm in running those again, but the big problem with that is that you will never find a test case other than what you're specifically looking for. So if you have a 200 test case document, then you will not find what would have been found if you had 201. And what I would say is that you would want to add in specific, especially the random testing, to broaden your test coverage beyond what you're expecting. The big benefit of fuzzing, I would argue, is that it gets you out of the specific, I know this might go wrong, and so I want to test for something broader. I know that SQL injection is hex 27. What happens if I test for hex 3E? Or 9C or something that's a little bit less commonly tested by people. I'll get to you in one moment. But what you would want to do is incorporate some of these techniques to broaden your test coverage outside of those original test cases. And if those test cases are things that look for flaw-specific things, you might want to organize those into the flaw-specific test suites and have them be selected also. I'll get back to you if you have another question, but question over here?
If you have 200 test cases, some of them might well include random testing, and then
Mm-hmm.
it's just a matter of hit or miss whether it hits, whatever it is that will trigger something, if there's something key there.
Mm-hmm.
And so usually, one of the things I always look at for adding new test cases or test suites is to look at what are known flaws, either the application if possible, or a particular class with the class is known.
Mm-hmm.
And if you bring up the slide, we have different classes. Yeah, any of them with the classes, different that, like that, okay? What I would always do for this, since we're never going to completely eliminate any of them, but we're going to go and prioritize it. You also prioritize it horizontally, as you can see with the percents, and vertically, as you can see with the arrows.
Yep.
I usually go for more of a decision tree type thing, where I'll have a particular test case that will be like, if this thing returns something bad, I should bang more here. So that way it helps me prioritize the tests. What do you think about that idea?
I think that that's actually a very similar approach to this idea, in that what the proposed thing was that you have more of a decision tree based way of selecting test cases than what was discussed here along the lines of probabilistic selection. I mean, certainly, one of the things that was blown over rather quickly but mentioned is that, using improved heuristics is something that can optimize and does optimize security test cases. I know that if I find a SQL injection with apostrophe, I don't need to start going and trying quotation mark, parentheses, comma, and all the other things. So I can certainly get rid of a lot of things there, and that's something that, hopefully will naturally be present in this system as well, because that apostrophe will bubble to the top of SQL injection test cases while the others go down. The one benefit I would say about that is that even with the decision tree, you're stuck with a lot of what you know, and the evolutionary algorithm can find things that are a little bit outside of it. Again, the escaping the local optima.
Well, the decision tree is just used for prioritizing based first on the fact that in either system you completely eliminate test cases, you prioritize it. So since it's used to start, and if you notice any indicators to prioritize, it doesn't mean you stop there.
Yep.
You do continue with time permitting and your random buzzing or what have you.
Well, it might be that we're talking about the same thing then. Any other questions? Right up here. Mm-hmm. Oh, yeah.
So that all the previous ones you hit already, you covered every time. So that, let's say you release a product, release an SP1 or SP2, you want to make sure that you don't do just evolutionary and long cases. Make sure that all the bugs you already fixed in the original one doesn't have to be as two different buckets of fixes.
Oh, most certainly, like a regression test suite and then a go out and find more bugs test suite. Yeah, most certainly. I think that I would not argue against going back and trying those old ones again. Again, if it doesn't, the one issue that often people fall into is that regression test suite becomes tens of thousands of cases that some person has to execute or that some person has to automate, and it becomes something where so much effort is put into that there is not as much effort going out and finding what's the new bug, what's the new evil thing to find. And so I think they're complementary, but you must take into account the limited nature of how much time or money can be spent testing things. Mm-hmm. Mm-hmm. Mm-hmm.
Because things might have changed, that some other weights might be of more value.
Mm-hmm.
So you might end up spending more time. Like having both sets is.
I agree. Yeah. The person asking the question is saying that having both static test cases and something that's more flexible, like an evolutionary system, are beneficial. And I would agree. You certainly want to make sure you cover your old tracks. Sun would have felt that was very important if they had looked at a certain telnet bug not too long ago. So, question right here.
Do you think that measures of robustness are just completely impossible, or just not possible now? Do you think I'm nuts? How do you think about this?
No, that's
Measure robustness.
the question is, the question is, how do I know when I'm done? Is it silly to think that one can capture robustness or security assurance? And is that fair?
Yes.
Okay. I would say that the measures that I've seen that are accurate are order of magnitude measures. We don't have a specific, you're secure now. Yeah, and so, but we also know that if I work with a client, and this is the first time they've ever called in a security expert, and they don't have anybody internal, and they haven't really thought about security very much, it's a bloodbath. You start off on request 1 or code page 1 or whatever else, and you find bugs all over the place. And that some of our other clients have put a whole lot of process into trying to address security flaws, and the amount of flaws that you find there is a couple of order of magnitudes lower. And so, what do you say to either one? Do you say the first one that, you have security flaws, you're not secure? Well, even the people with orders of magnitude less still have security flaws, but they clearly have benefited from the investment that they've made. And so it comes down to a lot of what are security metrics. Actually, there's a great book on it. I'll plug one of my former coworkers, Andy Jakewith, who came out with a book called, I think it was Security Metrics specifically, where he goes into a lot of detail on trying to capture metrics and trending, and it's the most comprehensive treatment I've seen on that. But in terms of when is security testing done, this is something that's a great question because we get it a lot, especially when people hire us. We show up for a month, we do our testing, and then we leave. And a lot of people would like that to be the end of their security testing, but that's never the case. It's always something you have to revisit. It's a moving target. Yeah. Question over here?
It's more about increasing your MTTF or mean time to failure, right? Let's say you're doing bus testing. When you start just random testing, every few seconds you might get an 80, right? As you keep fixing those, you can see that you ran for 2 days and you haven't found that many. Right? Still there's randomness there, but you get a sort of confidence that over time, it's not, again, at the end of the day, after doing like years of causing mistakes in one case, which might take over your server, still, the number of bugs and the you'll be able to see the trend and get some confidence. Yeah, just applying some kind of metric. I would feel that it's like
The difficulty of metrics is like anything else in economics. If you want to maximize one thing, then that will get maximized to the detriment of what might be called pragmatic security. So it's really a difficult problem. Yeah. It's what?
It's not a trivial problem.
It is an unsolved problem today. Yeah. Any other questions? Right up here in front.
What of the categories again? And one of the things,
The test suites?
yeah, the different categories, that one.
Yep.
For example, this is what you do with your regression suite. This is the data that you can use to start the training of it. You can see, historically, half the bugs you find are over in SQL injection. Obviously, your developers, at least over the course of the lifetime that was known, aren't very good at preventing it. So this will help in terms of categorizing an initial estimate. But one thing to watch out for is, let's say that management realized this, bought some kind of secure linter or something, and just completely nuked, say, all the format strings there. Then, even if you had a bunch of old test cases that are legacy, you're not going to find any new stuff. So that's when you have to adjust the temperature to reorder the thing. So being aware of, like they recoded the same thing in a new language. Well, you're going to have a lot of the same bugs. Some of the old ones will come back and so on. But you have to have some smarts on knowing how that's going to affect where you're supposed to be testing.
Was that a question or just a comment for the others? Okay.
Because with regression, you were mentioning how the regression thing isn't help, but it can be used just to prioritize it.
Yep. Well, any other questions? All right. Well, thank you all for coming and for your great questions, and I hope you enjoyed it.